Please join me in welcoming to the Distinctive Voices podium, Dr. Thomas Hall.
Hello there. Hi, good evening. Thanks for coming out, and thanks to the National Academy of Sciences for inviting me out here. This is my favorite subject to talk about, so I love talking about it. I'm going to talk about origami without too much feedback, hopefully. And my goal in this talk is to give you a sense of the math behind origami, also, what is origami, and to touch on some of the kind of amazing applications origami has found in the sciences, especially over the last 10 years or so. So, how many people here have done origami before? Wow, it's a little self-selective audience, I guess. But how many people have folded this before, this crane thing? Okay, yeah, it's a very popular classic origami model. And when we study an origami model, especially mathematically like that, we often try looking at something called the crease pattern of the origami model, which is what's shown there on the right. If you were to take that crane and unfold it and look at just the creases that were used to make that model, that's what you would see. And creases come in two types: mountain creases, which kind of make a mountain, and valley creases, which make a valley. Of course, if you flip the paper over, they all switch, but there's this still dichotomy you get there. So origami's really old. This is traditional, classic origami. There's a classic Japanese crane on the right, sometimes called an oritsuru, and a Japanese origami frog. Those models both go back to maybe as far back as the 1600s. No one really knows for sure, but they've been around a long time. They're wonderful to fold. They're very elegant models. But over the past 40 years, 30 years, origami's kind of gone through a renaissance. This is an example of modern origami, although I was reviewing my slides, and this says 1987. That's still kind of a while ago. But this is Robert Lang's Black Forest cuckoo clock. Robert Lang is an expert origami folder, especially with complex level origami. This is folded out of one piece of paper. No cuts. It's actually folded out of a rectangle, if that makes you feel any better. But what's also cool is if you pull the pendulum, the cuckoo comes out. But it doesn't tell the correct time, except twice a day. So here's some other examples. These are Kawasaki roses. They were invented by a Japanese mathematician named Toshikazu Kawasaki. These are cool because they look very curvy, but the crease pattern for these is nothing but straight lines. And so, there's this really neat interplay that origami can do. Even though when you analyze it, it looks very rigid and straight, you often get these very curvilinear type of forms. That's a very popular model in the origami scene. People love Kawasaki roses. As you can see, you can put one on each finger. This is another fun model. It's one of my favorites, Jung Maekawa's Demon. This is again from the 1980s, I think, in this Japanese origami book called Viva Origami. I actually have a couple of these. People can look at them if they want. It is possible to fold one of these. Again, no cuts. This is made from a square piece of paper. This one I'm holding here was probably from a 2-foot square, just to give you a sense of the scale of compression you get when you're making something that's complicated. But it's so cool. It's got 5 fingers on each hand and a tail and a tongue, and it's like, yeah. And that's the crease pattern. So, and there's a lot you can learn from this kind of stuff. There's, one thing that's fascinating is you fold something like this, and if you're brave enough, you can unfold it and look at the crease pattern. You can kind of see where the fingers happen. All those tiny little creases. That's where the hands are, and then these little fingers are what get formed there. But you can also go the other way too. If you want to design something like this, there's a method towards looking at designing crease patterns like this so that they will turn into the thing you want. That's kind of like another lecture for another day, but the process behind this rather complicated engineering task, like how do I fold a certain structure? Well, what crease pattern will give me that structure? That's kind of an engineering task. There's a lot of math in that. We will touch on that a little bit. But also notice, you see the same angles happening over and over again here. There are lots of 45-degree angles. There's some 90-degree angles, too. But everything here is made up of either 90, 45, or 22.5-degree angles. It's all divisions of a 90-degree angle, which is not that surprising. This is folded from a square, and those are easy angles to make. But there's a lot you can do with just that. I mean, this is wildly complicated. But if you think that's wildly complicated, look at this. This is more recent. This is circa 2002, I think, Satoshi Kamiya's WASP. I don't know how well you can see the details here. So there's the whole wasp, but if you zoom in on the head, you can see he even made like little, okay, wasps don't have toes, but they have little things on their feet, and he's got them. They're, whatever they are. And the abdomen is actually, okay, so before this there were origami wasps. People had made origami insects a lot, but this is so much detail, it's kind of scary. And the crease, if you look at the crease pattern, this is just on another level of difficulty than this. I mean, these are both complicated, but something else is clearly going on here that isn't happening here. I mean, notice, here you do have those angles happening over and over again. And here, well, you see those angles too, but there's other things happening too. Another thing that's going on here is that, and this is something that has emerged in complex origami like this. This is known as super complex origami, actually. Very few people have actually folded this, partly because there are no instructions. If you want to fold this, you have to go on the internet and get this crease pattern and hope for the best. And seriously, it's really difficult. But in order to get this great abdomen that has these plates, he's actually, that's the center part of the crease pattern here. And what Satoshi Kamiya is doing is grafting a crease pattern from another design onto this model he had for a wasp. In particular, there's a whole genre of origami called origami tessellations. This is one example. An origami tessellation, which I'm mentioning because this is a purely geometric and mathematical genre of origami. An origami tessellation or origami tiling is where the crease pattern is irregular tiling, okay? But it still allows it to fold into something, usually something flat. The purpose here is not to make a figurative model, like a goose or a bug, but just to make something that looks cool, you know? And you end up with these patterns of folds on the finished object. That's what Kamiya is doing here. He's creating this patterning by grafting it inside a more diverse crease pattern. It's like, the fact that you can even do that is wild. Yeah, so when I was in so this type of origami tessellation was pioneered by Sujo Fujimoto and he was actually a Japanese biology teacher. He's pioneered this in the 1970s, but more recently, like in the past 20 years, it's actually become a very popular branch of origami in the origami world. And when I was in grad school, procrastinating on my PhD, I got really into it. Again, these are designs I came up with. These are folded out of one sheet of paper. Here, no cuts again. This is a type of paper called glassine. It's a really thin, waxy-like paper. It used to be used to keep your postage stamps from sticking together, if you remember that, you know. And what's cool about it is that when you fold it, the different gradients you're seeing here are the different layers of paper with light shining through them. Okay, so you can see where the pleats are, and it really makes a nice stained glass effect. That's one reason why this area of origami is kind of popular. It takes a long time to fold these, though. It's great when you are avoiding work. Okay, but I want to give you all a taste of what origami math is, and at the same time give you a hint as to one of the tools that is used to design origami models like that. So for this, you're going to take your piece of paper. Okay, everybody hopefully got a square piece of paper. I have one here too. This one's mine. And you're going to either have to use your imagination or need a pencil or a pen, because you need to make a dot in the middle of your piece of paper somewhere. So I got a marker here. I'm going to do that. I'm just going to make a big dot in the middle. It doesn't have to be the exact middle. Just be somewhere in the middle. Although if you can imagine where a dot is, that's good enough too. But you need a dot or something. Okay, so I'll give people a minute to do that. What we're going to do here is a mathematical experiment. You're going to discover, this is what one thread in this talk is going to be a little personal to me. I'm a math professor. I teach math, and all my students kind of learn pretty soon that I do origami, and as soon as they find that out, they don't want me to teach math anymore. They want me to do origami with them. And so, I understand. So I sneak origami into classes, but they're doing math at the same time, and they don't know it. And it's like, I love that. So part of this is like that there's so much math in origami. You can actually use origami to teach math. Is like, what? Okay, so you're going to get a sense of what I sometimes trick my students into doing. Okay, so if you have a piece of paper and you have a dot in the middle, everyone's going to do something different, okay? What I want you to do is make a fold all the way through your paper, but it has to go through the dot. And I want you to be able to see the dot. So like, looking at the dot, you want to make like a mountain crease. And it can be anywhere, but it's got to go through your dot. And so you can do it at random, right? And then just make a crease, but you have to be able to see the dot, make it go through the dot. Okay, and then don't unfold it, leave it folded, and make your creases sharp. No wimpy creases. Be the master of your paper. Don't let the paper push you around. Okay? Some people are intimidated by paper. I understand it. It's Anyway, okay, so you've done that. Now we're going to do it again. You make another crease. Don't unfold it. Leave it folded, but it also has to go through the dot. And now you're folding several layers at the same time, so really use those finger muscles. Yeah. Okay? Now, again, don't unfold it. Now, if you've had enough, you can stop right there. Or you can keep going. You might, if you want, you could turn it over and do it again. Always make sure your crease goes through your dot. And you can just do a little crease, or you can do a big crease. Whatever you want to do. I'm going to do one more. And you can do another one. I leave it up to you how many times you want to do this. Try not to go crazy. Your paper isn't that large. If you have some origami experience, you might want to fold it maybe 8 times. I don't know. But it's up to you. At some point, you're going to have to stop, though. I'm going to stop here, because I know what's happening. Okay? When you're done, make sure your creases are sharp. What I want you to then do is unfold everything. Unfold everything. And what you should have are a bunch of crease lines coming out of your dot. Here's what I want you to do. Count how many of those creases coming out of your dot are mountains and how many are valleys. Okay? And I'm going to keep track of this. And I want people to tell me how many mountains you have and how many valleys you have. Anyone feeling brave? Want to tell me? Yes? Yes, sir. 5 mountains, 3 valleys. 5, okay, got to click here. 5 mountains, 3 valleys. Okay, anyone else get different numbers? Yes, on the corner there. 4 mountains and 2 valleys. Or 2 mountains? Okay. Should I write that separately? 2 mountains, 4 valleys? Well, if she turned hers over, you get the same thing as yours, right? So that's kind of the same thing. But did anyone get something different? Yes? 6 and 2. Count again. No, yes, next to you? 7 mountains and 5 valleys. 7 and what? Ooh. Double check that. And any other numbers? 9 and 7. Yes? 6 and 4. Okay, 6 and 4. And then 9 and 7. Notice I've avoided some numbers, and it is sometimes possible to make a mistake because it's well, again, there's the sharp crease thing, but also sometimes it's creases get hidden and stuff, especially if they're on top of each other. But what's the pattern you're seeing here? Yeah? Does what have to be even? Because I see 7 here and 5. Oh, they always differ by 2. Yeah. I mean, it is true that if you add them together, you always get an even number. That's true. But the thing I was hoping people would notice, there's actually a lot of things you can notice in exercises like this. This is like a neat little mathematical laboratory. There's actually a lot of math you can discover or experience with this little activity. But the thing I was hoping people would see was that, yeah, the difference is always 2. That is a theorem. Ooh. It's called Maekawa's theorem. The same Maekawa who invented this devil dude. he's also a physicist, a Japanese physicist, and he is one of the people who first discovered Maekawa's theorem, which, if we state it formally, goes like this. So notice that these things we folded, this is an example of something called flat origami. It's origami that you could press in a book without crumpling or adding new creases. A lot of origami that you see in books is flat origami. You know, you fold, 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 and you get something flat, and it looks like a bird or whatever. So if we looked at the crease pattern of a flat origami model, and we look at one vertex, I say, let V be a vertex of a flat origami crease pattern, and let M and V be the number of mountains and valleys coming out of that vertex, then we always have this. M minus V is going to be either +2 or -2. +2 if you have more mountains and valleys, or -2 if it's the other way, depending on what side of the paper you're looking at. You know? Now, against perhaps my better judgment, because this is a public lecture, I want to prove this. Okay, I want to do a math proof, and it's not as easy as you might think, because one slightly deceptive thing about this exercise I had you do is we started with a crease that went all the way through the paper, right? That doesn't have to always happen. I have an example here of one. Here's a crease with a vertex with 4 creases coming out of it, but none of them go all the way through the paper. So this can happen, and you see this in a lot of origami models, actually, this kind of thing. So it isn't as easy as saying, well, the first crease was 2 mountains, and then every crease after had a mountain and a valley. That'd be a nice, easy proof, but that doesn't explain why this works too, or other things are perhaps even more weird. So here's a quick and dirty proof that I like, because it uses a fun proof technique, as you'll see. Although it's a little sacrilegious, because we're gonna use scissors. I know, the title I promised no scissors, but still, it's imaginary scissors, maybe. So you take your origami vertex, whatever it was, this thing, and you fold it flat, okay, and you leave it folded, and then you cut off the vertex. And then without unfolding, you look at this cross-section, the cross-section of what you cut. And that's going to make some polygon, but it's flat. Okay? Here I made it not look flat so you could actually see something. But I want to investigate that cross-section when you cut your vertex. Okay? Now here's why I like this proof technique. This is called proof by monorail. Okay? This is supposed to be a monorail. It's not a purple finger with teal nail polish. It's a monorail. And monorails go around their tracks. So here you're imagining this monorail going along the top of your cross-section that you cut out. Okay? And the question is, what's it going to do as it hits these corners? Because remember, this is supposed to be flat. All right? I'm making it look like a cartoon so you can see what's happening. But as this monorail, it's going to hit this crease, and then it's going to have to rotate 180 degrees. Right? Because this is flat. And then it's going to hit this one and rotate 180 degrees. And then it's going to hit this one. And it's going to rotate 180 degrees, but in the other direction. Now, what's the difference here between that corner and these other corners? Yeah, the difference is exactly mountains and valleys. If we were, for example, here, if we were looking at it from above, then these would be mountain creases here. And we'd hit a mountain crease and turn positive 180 degrees, and then positive 180. But then we hit this valley and turn minus 180. That's the key. That every time we hit a mountain crease, we're going to rotate positive 180, and every time we hit a valley, we'll rotate negative 180. Now, what's the total amount we'll turn when we come back to where we started? 360, because it's really just like going around a circle, except we have these sharp corners. So, 180 for every mountain crease, plus negative 180 for every valley crease must equal 360. Bingo, you divide by 2, you get MIS radius 2. Yay. Now, that's if we were looking at it from above. If we were looking at it from below, we would have had 180 for every valley and minus for every mountain. So you could have gotten V minus M is 2, and that would be minus 2. Yeah?
180 is you reverse your direction. If you really turn 180, you'd be going back where you came from. Those angles aren't 180, are they?
Yeah, they are. No. Remember, this is supposed to be flat. I've just made it look kind of bowed out because it's a cartoon. And it'd look really boring if it was just all on a straight line, like it really would, right? And then so to see what's happening, you're imagining. But yeah, these are supposed to be flat 180. But good question. Cartoons are sometimes evil. But yeah, so there's a proof. Woo! Okay, so some other origami things. There's so much math in origami. a lot of it is geometry, which makes sense, right? You're folding, you're making straight line creases. Well, one thing that's really kind of interesting to do is compare origami with geometric constructions. Like every time you make a fold, you're making a straight line, and you're making creases intersect, and that's locating points or vertices on your piece of paper. That's exactly the same kind of do when you do straight edge and compass constructions. You're creating lines, you're creating angles. So you can actually play the same game of like, well, what kind of geometric objects can I construct by origami? In the same way we would say, what kind of geometric objects can I construct out of straight edge and compass? Just like the Greeks did 2,000 years ago or more. Yeah. But what's funny, so this is a fun game to play, is that you can explore lots of geometry just by thinking of origami as constructing lines and points. What's interesting is that it turns out that origami is more powerful than straight edge and compass. There are things, if people, when you learn about straight edge and compass, there are certain things that straight edge and compass can't do, like trisect angles or double cubes. There's a couple of classic Greek geometry problems that stymied the ancient Greeks because straight edge and compass, it didn't seem like they could do them. And then thousands of years later, people proved it was impossible to use straight edge and compass to divide an angle into 3 equal parts in general, or double the volume of a cube, or solve cubic equations. But origami can do those things, it turns out. And I could do a whole lecture on just that, which if you really like geometry and algebra, it's cool. But that's one of a pretty deep area of the geometry. It's kind of showing that origami is powerful, okay? Here's another geometry thing. This is called Kawasaki's theorem. This is the same Kawasaki that did that rose I showed you, Toshikazu Kawasaki. He was one of the people who discovered that, hey, if I look at a flat origami crease pattern and I focus in on one of the vertices, then there's a really neat relationship between the angles. And this, you could even unfold yours and find this too, although maybe it's hard to see it with your eyes. And the relationship is that, well, if you have 4 angles, then if you add up every other angle, like alpha 1 here and alpha 3, you're going to get 180 degrees. If you add up the other pair, alpha 2 plus alpha 4, you're going to get 180 degrees. Same thing if you add more angles. You'd add up every other one, all the even ones, and they'll add up to 180, and all the odd ones will add up to 180. Or another way to say that is that if you do the alternating sum of them, if you subtract these 2 equations, you'll get that these minus those will give you 0. That's called Kawasaki's theorem, and it's a great way to actually check if your vertices will fold flat. Yeah, so that's another geometry thing. But there's more. So there's a branch of math called graph theory. It fits into another branch of math called combinatorics, which is about just counting things. Graph theory is about networks. So if you look at an origami crease pattern, it's actually a network of points and lines. You can just study, like, well, what properties does that have? How many of you have heard of something called the 4-color theorem? Or the map? Yeah, very enthusiastic hands shot up here in the front. Awesome. That's a very famous mathematical problem. It says if you take a map of the United States or a map of any bunch of countries, and you want to color the countries with as few colors as possible, but you want to obey the rule that 2 countries that share a border should not get the same color, right? Or 2 states that share. Otherwise, you'd have like California and Nevada both being like purple, and then people would think that Las Vegas was in California, and you can't have that happening. So bordering states or countries have to get different colors, and it turns out, and you can prove, that you never need more than 4 colors to color any map that way. That's a hard thing to prove, it turns out. It's very simple to state, but very difficult to prove. It took people about 100 years to prove that, and they needed computers to do it. So, interesting question. Suppose I look at my origami crease pattern. I can view this as, pretend it's a map of states. How many colors do you think I need to color it? Well, 4, yeah. You know you can do 4. You can actually do better. You can do it in 2. You can always do it in 2. That makes mathematicians excited, because they're like, hey, that's cool. I can actually offer you a proof, but, well, a very hand-wavy proof. See, look here. Here's the same crease pattern, but it's colored. What's it going to look like when I fold it back up? This is the crane. Ooh, I've got some smart people in the audience here. They're muttering something sensible. I'm going to start folding this. See, this was in my luggage, so it doesn't want to fold anymore because it's all been flat. But I'm going to make it. Come on, paper. Here we go. Okay, so I'm starting to fold it. This is the bird base, if you've ever folded one of these. And then I make the head, tail, and I make... Does that make sense? Because everywhere there's a crease, you got two different colors. And each crease is forcing those two neighboring faces to point in different directions. So the fact that I can two-color is completely the same thing as the fact that this is flat, right? That has one side and another side. Those are the two colors. So this is kind of cool. I love stuff like this because this is what math is about. It's studying structures and things in the natural world and expressing them with theorems and things that you can prove. And that's kind of what origami is all about. But there's more, of course. Now, I'm only going to go over this kind of stuff a little bit because not everyone here has had linear algebra. But you can use matrices to study origami. Okay, so what's this? This looks weird. This is a three-dimensional origami crease pattern, or a crease pattern that makes something that's three-dimensional, not flat. I think I have one of those here too. Let me show you what this is. So this has like 5 crease lines, and notice that I've labeled each crease line with angles. Those angles are telling me how much I should fold them, and some of them like how much should I bend the paper. So here it's saying I should bend it pi. Okay, that's 180 degrees. So this has to fold all the way over, 180 degrees. This goes minus 180, that's a mountain crease. But these only go 90 degrees, so they're going to make right angles. Okay, so it ends up looking like this, like a 3D corner. Okay, now what's cool about this is that if you wanted to model this mathematically, this is a little different. It's in 3 dimensions now, right? It's not quite the same thing as all the other examples we've seen. But you can model what the paper's doing by imagining doing something like, let's see, I should orient it like there. Like imagine I fix one of these faces, one of these regions of the crease pattern. Then I can model what all the others are doing by imagining them rotating about the various crease lines. And you can model that with these things that are called rotation matrices. I can imagine like this being in the xy plane and the corners of the paper having coordinates, and I take one of these coordinates and multiply it by that matrix, and it would tell me where it goes under a certain rotation. And then I could see where this corner goes and that corner. And you can model all this stuff, and I'll actually have some cool animations that show you how you can model this on a computer. But it uses things like that. And what's cool about it is that, well, there's this theorem that was first observed by Kawasaki in I think in the 1990s. But he didn't prove it. It wasn't formally proved until a little bit later by myself and a collaborator of mine, Bel Castro. But if you were to take one of these vertices that makes a 3D origami model, and you figure out all the rotation matrices for each crease, and you multiply them all together, that's what these things are. These are just, each one of these is one of these matrices that rotates about a certain crease line. Okay? If you multiply them all together, if this actually works as a crease pattern, that's something you can fold, then the product of those has to be this, which is called the identity. And that's the matrix that does nothing. And if you think about it, that makes sense, because if imagine you were an ant, and you were crawling around on this origami crease pattern, because why wouldn't you if you were an ant? And you start somewhere down here, and every time you cross a crease line, you're going to rotate, right? And you'll follow one of these matrices. Well, when you come back to where you started, you've done nothing. You're back to where you began, and that's kind of like getting the identity. That's not really a proof. It's brushing some details under the rug that I can do because I'm on stage. But this has some really neat things going on with it. What this is doing is capturing something that mechanical engineers call rigid bar kinematics. That is, this matrix product is actually capturing what happens, not just how I can fold this, but what happens as I open and close it. Like, in particular, what are the relationships between what's happening at all the creases as I open and close it. Being able to do that kind of thing and to be able to model that with origami is actually very exciting to engineers. Because if they can take equations like this and understand how all these things work, then that means this might be something they could use in a mechanical moving device of some kind. Which may not sound all that exciting, but it will when it will in a moment. So like here's an example. This is a computer animation of a vertex, a flat vertex in this case, opening and closing. These numbers here are the angles the folding angles of all these creases. So here, imagine it's not completely folded because I want you to be able to see the layers. But so like this folding angle here, that's phi3. That's almost negative 180 degrees. Okay, it's practically 180 degrees, and that's because I guess that from this angle or this side, that's looking like a mountain crease. And these are looking like mountain creases. They're also close to negative 180. But there's a valley crease in there that's positive. So if I let this run, notice how all those folding angles are changing. Wow, until it comes back and folds the other way. Now let's see if I can slow that down. So if I go to the unfolded state, right there, all the folding angles are 0. Nothing is being folded. Okay. But if I move it to a position like this, notice the pattern here. These two are the same. And those two are the same, except, well, they're not really. They're complementary. One's a mountain, one's a valley. Okay? So what is this? This is phi1. That's this crease here. It's got this folding angle around 68 degrees. And the one opposite it is phi3. That has the same folding angle. This is something you can prove. I'm just demonstrating it with a computer model. But you can prove that if you have 4 crease lines making a fold like this, then the opposite folding angles are going to be the same. And that relationship you can totally derive from this equation here. Well, except we'll only have 4 matrices. And you get these great equations that look kind of crazy. Okay, so these are the first 2 I've just described. Like you'll have 2 of these being equal and 2 of them being complementary. But what the hell is this? Well, that's me trying to describe. Let me pause this for a second. Describe, okay, that's great. We see that these are the same, but what's the relationship between like phi1 and phi2? Or phi3 and phi4? Is there any way I could predict what phi4 is going to be if I knew what phi3 was? That's the kind of information engineers would like to have if they were going to really use this in that application to predict how it's going to fold at all the creases at any point in time. But again, using that matrix product, you can get equations like this that are kind of crazy, but they tell you the relationship of here phi1 and phi2, 2 creases that are right next to each other. Now this may look weird, but if I rewrite it like this, it's actually a really nice relationship. And I know this is not a math class, but I just want to point out something. Here, what I care about is phi2 and phi1. Those are the 2 folding angles that are right next to each other there. Okay? This crazy thing is a constant. It doesn't change. Look, alpha 1 and alpha 4, they're just the angles here of my paper. Those don't move. Those angles don't change as I fold and unfold. This is like, I don't know, like 45 degrees, and maybe this is, I don't know, like maybe, well, that looks more like 60 degrees. Maybe this is 70 degrees. I don't know. But that won't change. This is a constant. And this, okay, I had to take tangent of this angle over 2. That's weird. But what this is showing is that if I do this tangent of the half angle there, I get a nice linear relationship between these folding angles. Engineers and physicists love linear equations because we can model them. We understand how they're supposed to work. And yeah, we had to stick these trig functions on it, but still, that's very surprising. And it's telling us exactly what's going on. Okay, and that's what we use it's equations like this that are actually the equations that we use to model how to fold these things and to create computer animations like this. Now, what's also fun is that I can give this kind of stuff to my students. I already said that, but I have to kind of like brag a little bit. This is an animation of not just 1 vertex, but 4 vertices folding together using the same types of equations, but more complicated because there's more creases. But this was made by a summer student I had named Kai Shi, who, he lives in California, actually. But when he was in high school, well, okay, he's still in high school, but because this was only last year, he came to a summer program that I teach at, that I should give a plug for, where I teach a 2-week-long course on origami math to really smart high school kids. And by the end of that class, he was able to make this animation using exactly the type of math that I showed you. But he's really smart, so he was able to do it really fast and make something really pretty. Like, I like this because this is on a computer. This isn't real, so we can pretend the paper's passing through itself. It's like ghost paper, you know? Like, notice right here. It's like, real paper doesn't do that, right? Yeah, so, you know, to brag, I had to show you some pictures. These are kids taking my origami math class in the summer of 2015. That's Kai, that's the guy who made that animation. But here they're talking about vertices and how they might fold. Here I think if you read carefully, they're talking about straight edge and compass constructions and origami constructions and arguing with each other, because that's what you do in math. You make conjectures and you argue, and then you may fold some fractally wave things. That's what they're doing. And I forget what these people are doing. Something having to do with, I think, analytic geometry in origami, maybe. I don't know. But, yeah, if you know any fun high school kids who love math and maybe like origami too, you should point them my way. Because I am such a strong believer in pushing young talent. I don't think there's enough support for kids who are really smart in math or science to really take their talent and run with it so that they can be not just really good like they already are, but awesome and world leaders. I've been teaching in programs like this since 1991, and I've seen the difference it can make with really bright kids. So, point of personal, I don't know, gumption or something. But just to kind of hammer the point, look, I tried to make a list of math topics that you could use to either teach math in origami or just to explore origami. I already talked about a bunch: geometry, matrix algebra, graph theory, but also statistical mechanics. What's that? It's something hard that physicists use in polymer folding applications and stuff, and I understand it a little bit. I mean, math is huge. It's hard to know a lot about all branches of math. But that's hard stuff, and it has actual applications to origami. Analysis. People have studied using like differential equations and stuff to see how origami continuously folds and unfolds, and also to try to address a problem called the self-intersection problem. Differential geometry, that's another kind of geometry, but now we use calculus at the same time. Some of the properties that I mentioned before can be best tackled with differential geometry. Or topology, where you say, hey, I don't have to fold paper. What if I folded a sphere? What if I folded a donut? Or, you know, what if we fold other things? Those are called general manifolds. We can actually talk about folding them in the same kind of ways. There's equivalent theorems to Maekawa and Kawasaki's theorem in other dimensions and other types of surfaces. It just never ends. I mean, the spread of math in this subject goes from what you would learn in high school or even grade school to what you might learn in graduate school. Yeah. So I actually wrote a book about this called Project Origami. That's a book for teachers on how to use origami to teach math. Hey, if you're interested, I wrote it, so I like it. But I try to put jokes in it too. So even if you like jokes, you can do that. Okay. So what are we doing with all this? I want to address this question. There's lots of things you can do with origami. And I want to explain this, but before I do, let me explain something much more simple. And we will see this again. I'm holding in my hands a very famous piece of origami. It's called the Miura map fold. This is something designed in either the late 70s or early 80s, depending on who you talk to, by a Japanese astrophysicist named Koryo Miura, who was looking for a way to put solar panels in outer space. You want solar panels to be big, but rockets are kind of small, or at least the tops of rockets are small. So you can't just put a huge solar panel on the top of a rocket and shoot it off into space. But you could try folding it. And so he came up with this origami model that takes a small thing and expands it into something really big. And what works, so you can imagine each parallelogram, each piece of this being a solar cell, except maybe a lot bigger. And then you could collapse it into something that could conceivably be part of a rocket that you shoot up into space. But then you need it to unfold in outer space without the help of human hands. And that can be a problem. Like, how do you know that how would you program this to unfold on its own? You know, that's something I'm going to address at the end of the talk today. That's one application. That's an example of an engineering type of application. More recently, though, in the past 4 years, I've been working with a team of physicists, Ryan Hayward and Chris Santangelo at the University of Massachusetts, very close to where I work, and Itai Cohen at Cornell University. And Ryan and Chris, in particular Ryan's lab, came up with this technology, this way of getting tiny, microscopic-sized polymer gels to self-fold, okay? And using the following technique. What they do is they tri-layer, they sandwich 3 layers of polymer. On top and bottom, they have a rigid polymer or plastic, like some kind of polystyrene on the top and the bottom. But in the middle, they have a spongy type of polymer. In fact, it's the same type of polymer that you see in grow animals. You stick them in water and they go bloop. So the stuff in the middle, if exposed to water or heat, they have the special kind that can react to heat as well, it will swell. But we sandwich it with this stiff stuff that won't swell. And then we carve, like on the top, we carve these crease lines. And and here you're seeing a cross section, so you're seeing like one channel of one of these crease lines here. And if we pour water over this, this will swell and make a mountain crease along that channel. So if we put gaps on the top, it'll make mountain creases. If we put gaps on the bottom, it'll make valley creases. And this is actually an electron microscope photograph of us testing this out. The width of our crease determines how much it folds, what the folding angle will be. So this gives us a lot of control of how to get something really tiny that we can't fold with human hands to actually fold. And look, we can make it fold all the way, like a full 180 degrees or any other amount, and we can program it to do that. Yeah, so here's a picture of a Miura map fold unfolding. This is less than 1 millimeter wide, okay? It's going to unfold and then it's going to fold again. So this is it like drying out, and then we get it wet again or heat it up or whatever we did, and then it folds up again. So we can like fold and unfold these things. They're not one-time operations. We can actually like do this all day if we want to. Yeah, and people love the Miura map fold. So the fact that we got that to work made people really excited. But then we had to actually do some origami, right? So we took a variation on Randlet's Flapping Bird. This is what it looks like in macro scale if you fold it out a piece of origami paper. But this is our tiny, tiny version. If you want to see how small it is, there it is right there. This thing there, that's a grain of rice. Okay, there it is. You can see, it actually looks like a little bird. We think this might be the smallest folded crane ever. We're not certain, but we think. We haven't gotten Guinness to come out and look at it. But this actually works well. And then they wanted to fold something really complicated, so I came up with something. This is another complicated origami tessellation, but this folds into something 3D. And here I'm trying to describe it, but it's complicated. Anyway, it worked. Well, it kind of worked. This was really hard to fold. That had over 200 creases in it. And here's it unfolding. Let me run that backwards. So if we imagine it folding, then it would go in this direction. It's really hard to film these things because they're so small. And they pop out of the plane, and then they get out of focus. But notice that I had a little trouble here. This part folded really well, but this part didn't. This is actually sped up. This whole thing here I think this was like a half an hour of it unfolding. But we're worried about this part here, so we let it sit in the solution, the water, for like I think 4 hours, and then it all came together. So there's a lot we still have to learn about this. All these creases were like fighting with each other to get into the right positions and stuff. There was clearly mechanical tensions going on that we didn't predict in this. But the fact that we could even do this is amazing. There are a lot of engineers working on self-folding things, both for things like the Miura map fold to make satellite things, and also for small things like this. One reason why this is exciting is because this is made out of soft polymer gel. It's water-based. It is biocompliant. You could stick this in a human body and it wouldn't care. So the applications are many. You could imagine making an origami thing that would encapsulate, like an origami ball, that would encapsulate some drug, some really toxic cancer-killing drug maybe, and aim it at a tumor and have it open up in response to heat or something that we could program. And thereby, instead of poisoning your whole body with something toxic, we poison just the parts we want to kill. Targeted drug delivery is what it's called. There's many different research groups trying to do that kind of thing. Origami could be a solution to that. There are other types of origami structures people are using for artery stents, ways to clog, or you could imagine, engineers are really excited about origami because it gives us mechanical ways to make things move at perhaps a really, really tiny scale. It's hard to make robots that small because mechanics just doesn't work that way. You can't make like a little metal robot and make it like less than 1 millimeter wide. The mechanics breaks down. But origami continues to work, it seems, if you choose the right materials. And so maybe we could even harness what we're doing here to make little mechanical devices that could do things like unclog arteries or something. There's a lot of potential applications here that could be pretty surprising. Okay, I want to talk a little bit more about self-folding. This is a computer animation of the mirror map fold again. And there's this question of, if I design something like this and I want it to unfold on its own, either in outer space or inside the human body, how do I know it's going to fold properly and not do something bad? Here's an example. So this is work that I've been doing with a really smart Japanese mechanical engineer and paper folder named Tomohiro Tachi at the University of Tokyo. And one example of how things can go wrong is this. This is just a hexagon-shaped piece of paper with mountain creases in dark and valley creases as light lines here. This could fold, this mountain valley crease pattern could fold in two ways, either pop up or pop down. And it has the same, notice the mountains and valleys don't change. It's just saying, okay, I could fold those mountains and valleys like this or like that. Okay, and if all I wanted to do is program the creases to be mountain, valley, how does it know, and it was starting from a flat state, how does it know whether to pop up or pop down? The creases by themselves don't know. They're just like, I want to be a mountain. But the vertex is deciding somehow to go up or down. And how do we control that? That's the kind of thing we were seeing happening here. Okay, like with this area that was getting all kind of mussed up. There were vertices that didn't know what they should do yet. So how do we control that? This is a big problem. In order to tackle it, Tomohiro and I had to come up with a mathematical model for what self-folding is, and try to harness it, or try to make a model that we could have some control over. So for this example in particular, we had two modes. We could either go from pop. So imagine we start with this. We want to go pop down. We have all these mountain creases here, valley creases there. We want them to unfold to the flat state and then into this pop-up state. So here, this mountain crease is changing from mountain to flat to valley. And so imagine we want to make that self-fold for some reason. Okay? Well, the danger would be, instead of going along this path, what if we went that path instead? Because notice, this still also has a valley crease there. So our mountain would be turning into a valley, but it's going back to pop down instead of pop up like I want. How do I control that? Well, here's how. By doing a bunch of math, we can find relationships between the folding angles that we have here. Here I'm assuming my vertex is completely symmetric, and I have all the mountain creases have the same folding angle, all the valley creases have the same folding angle, just to see if I can do this. And what we do is create these curves that tell us the relationships between these folding angles. So this pink one, maybe that's the desired folding path I want to take. But there might be this other one that I could accidentally go down. Okay? Well, if you think about it, if I'm going to program this to self-fold, what that means is I have some mechanical device at each crease that is lending a force to that crease. Right? There's some force, there's something. It may be my gel swelling in the polymer gel stuff, or maybe there's like a little motor in there that's saying, hey, let's make you a mountain. But it's giving some force to that crease, some angular momentum force. Okay? And so if I'm at some point on this curve and I want it to fold, what I'm really doing is pushing these folding angles in some direction with some vector. Okay? If I want to be able to go to the center point there, that's where our folding angles are 0, that's where we're flat. If I want to be able to not go down the blue path, but to continue along the pink path here, then I want my force vector to be at right angles to the blue curve, right? Because if it's at right angles, and this is the direction that these folding angles are being pushed, then there's no way it'll go down either up or down the blue path, because it's like kind of going perpendicular to them. It's not, the force will not take it down there. It'll still instead take it down the path I want. So we want, in order to make self-folding work, we need to find just the right forces to make all the creases go along the paths that we want them to go. And that sounds kind of simple, but it's led to something very surprising, especially in this example here. So this picture looks kind of dotty. This is strange because it looks better on my screen. But here are the actual curves that we get here. And So I wanted to go along mode 1 here. Yeah, this blue mode in this example. So I wanted this vector, remember this vector tells me what force I should give the creases, both the row 1 and the row 2 creases here, the ones that are mountains versus the ones that are valleys. And this is the right vector to make it perpendicular to the pink one, so it'll just travel along the blue one like I want. That's this top mode 1, okay? But look at this. So we actually calculated this. We had to do some calculus and calculate it. And we got the force had to be parallel to this vector, 2 plus square root of 3 in the x direction and 1 in the y direction. But notice what that means. These are both positive numbers. This is both pushing the creases to all be valleys. That is really counterintuitive. If I was going to try to program this just like naively, I would have said, oh, I want this mountain crease to turn to a valley. Okay, I'm going to push it with a positive force. I want this valley to be a mountain. I'm going to push it with a negative force. Because mountain creases have to be negative, valley creases have to be positive. That's how we're measuring things. So you would think you would need like positive force, negative force, powers. You'd think you need to alternate. But this is saying no. If you want it to self-fold properly, you need a strong positive force and then a weaker positive force. And that will push it through this singular point at the origin. Tomohiro and I did not expect that. And so we had to test it out. This is Tomohiro's hand. He made a metal model of this. And you can see here, this is a weak crease. It only has 2 spring hinges. They're like creating a force, whereas these have like 4 of them or something. And he's calibrated them to mimic those, the things we calculated. And here is him trying to, so he lets go of it, and it pops up like it should. But then he picks it up and tries to push it in the wrong direction. And watch what happens. He tries to invert it, and it still pops up. So it's working. It is not getting caught up in one of those bad states. So this is kind of amazing. We didn't expect this at all. But so if anyone wants to do this kind of thing, now we have a way to try to give them something so that they can predict what will work and what won't work if they're going to make a mechanical device out of these kind of things. Okay, I should wrap this up soon, but there's a couple of more things I wanted to say. The moral here is that, the math of paper folding is surprisingly deep. There's so much math that you can do with origami. I hope you got a sense of that today. And the applications of this are kind of unexpected. They go all over the place, too. But I also wanted to say a few things that are kind of pertinent to the times here. The research that I just described to you about self-folding, as I said, that came between a collaboration between myself and Professor Tomohiro Tachi at the University of Tokyo. He and I first met at an origami convention in New York City, I think maybe 7 years ago. There are origami conventions. We get together, we have fun. It's kind of amazing. But this and he and I meet now regularly at conferences in the United States and in Japan when I can manage to travel there. But this kind of international collaboration is very common in math and science. In fact, the reason why I'm here, I live in Massachusetts. The reason why I'm here at the National Academy of Sciences is because there's a weekend-long science symposium that is jointly sponsored by the National Academy of Sciences and the Kavli Foundation that is bringing together scientists from the USA and Japan to discuss exciting advances in a broad range of disciplines in science. It's an international, interdisciplinary exchange of ideas that we do. The fact that the USA promotes and funds these kind of international science exchanges is one of the reasons why the United States of America is considered a world leader in scientific advancement. Our university system in the United States is considered among the best in the world. And a big reason for this is that we have people from all over the planet that are coming to the United States to learn at our universities and do research at our universities. We have a long history of making such academic international collaborations easy. In fact, if it were not for the support of places like the National Academy of Sciences and the Kavli Foundation and the National Science Foundation, which supported a lot of this work that I've done, much of this research that you saw here just wouldn't have happened without that kind of support. And it's interesting because, the United States and Japan have not always had great relations. 60 years ago, I would not have been able to work with Tomohiro. It would not have been allowed, right? And we shouldn't forget that not that long ago, researchers couldn't work with people in the former Soviet Union. That was not allowed. Political winds change, and when they do, we must be ever vigilant to protect, encourage, and support collaborations with scientists from around the world. Simply put, we cannot be a world leader in science and math if we do not allow ourselves to collaborate with the rest of the world and for the rest of the world to collaborate with us. It's one of the things that makes America great. Case in point, origami is a Japanese import to the United States. Thank you very much.